Okay, so last class we saw that we could solve first order differential equations through the use of the integrating factor, which was just equal to e to the 1 of the functions d at x, and then we could solve using the integration factor. We also saw that we could solve homogeneous second order differential equations. For example, something like this equals 0 by just using factoring out the a, b, and c terms and solving for the roots of those. And then we saw that there were three scenarios in between them where there was the two real roots, which gave us two answers. And then this answer was in the form of y equals a to e to the r1, b e to the r2x. We saw two real roots there. We had one real root where we also, instead of the b e to the r2x, we had bx e to the r1x was a solution. And then when we had imaginary roots, it was in the form of sine and cosine. And since I didn't memorize that, although it's right up here, right here. So we've gone through a few differential equations and how to solve it. What we're going to touch on today is non-homogeneous equations, as well as talking about exponential growth and decay. So for non-homogeneous equations, instead of having that zero term, basically what we have is another function of x that we can't isolate. We can't take that away and make it something different. In this case, this is these n's here are the order of the differential equation, so it could be of order n, and then the y's are or the functions. F is a function, so there's different functions. So function n minus 1, function 1, function 0, and they're a function of x, or they could just be a constant. But typically what we want to deal with is if we want to know how to deal with the ones that aren't constants. So what we want to do is we get two solutions. We get the yc, which is the solution to a homogeneous equation, but all we do is remove that rx, and we solve for the homogeneous equation. And then yp is a particular solution to the, actually that should read non-homogeneous, that's a typo. And we'll see through an example here. So if we just take this example and we remove the rx term, then we know, because now it's a homogeneous second order differential equation, we know that the solution comes in a form of this. So we can actually say that y is equal to if p at x and q at x are constants, we could say that it's in the form of this form, like we talked about yesterday, right? If they're not constants, we have to find a solution to that, and I'll get down to that later. So the first one we do is we find the solution to the homogeneous equation, and then we can go on and calculate a particular solution to the non-homogeneous equation. So if we go through and we say, for example, that we're dealing with this second order differential equation, we say the homogeneous equation becomes this here, y double prime plus y equals 0 instead of y double prime plus y equals x. So two solutions that we could use are y1 equals cos x and y2 equals sine x. If we put that into the solution as our yc, we can show that y1 prime is equal to y1 sine, it's a negative sine x. I gotta look at my notes here. Negative sine x, y1 double prime is equal to negative cosine x, and then y2 prime is equal to cosine x, and y2 double prime is equal to negative sine x. I'm going to have to check on that. I'm going to do that right now. Okay, so yeah, that's right. Cosine and sine, the derivatives of those work together. And we can plug them back in to the original equation, and we'll find out that this equation here, we'll find out when we do y is equal to, or sorry, we plug it back into the original equation. I'm getting ahead of myself here. And we get that y double prime, which is cosine x, y1 double prime is negative cosine x times y, or plus y, is cosine x equals 0. So that's a solution, right? Just 0 equals 0. And then we do the same for y2, and we get y2 double prime is negative sine x, and y2 is sine x, and we're going to get the same thing, right? So 0 equals 0. So that's good. We've got two solutions which are independent of each other. The definition of that is that the solutions of the functions is not equal to 0 at the same time. Don't worry about that as long as they're not the same. We can't just say y1 is cos x, y2 is sine x. And then what we do is we need to find a particular solution to the non-homogeneous equation. In this case, it's quite simple. Not quite simple, but it's simpler because the differential equation is simple. And we're just going to try y equals x. So if y equals x, then dy by dx is equal to 1. And then d squared y over dx squared, or the second order, is equal to 0, right? The derivative of a constant is equal to 0. So we plug that back in to see if it works into this equation. And we get y double prime, which is 0, plus y plus x equals x. And that works. So therefore, all we do is we put our solutions into the form of this here. So all I've done down here is I've got the complementary solution, the particular solution, and I put them in. So C1, so some constant times, which y1 was cosine x, plus C2 times sine x, plus x equals y. And we can take the derivatives of all of those and plug them back in and check it to make sure it works. We do that here. So I took the derivative of that, all the solutions here, and then I plugged them back into the original equations and got x equals x. Because the negative cosine here cancels out that one, and the negative sine here cancels out that one, and we're left with x equals x. Therefore, is our solutions value. We're going to go over how this works with civil engineering later, but right now we're going to go. We're just going to carry on with exponential growth and decay. So, nice part about exponential growth and decay, and maybe this should have been put into a different section when we were talking about separable equations, but I didn't, so I just left it here. But the nice part about them is they are separable equations. So what they're typically written in the form of is that there's a change. If we take exponential growth, there's a change. We're looking at the change in a population. So P equals population of no matter what. It could be bacteria, it could be people, it could be wombats. I don't know. It could be anything. And it's basically changing over a function of time. K is a coefficient based on some sort of data collected, usually birth rates, death rates, a ratio of that kind of thing for human population or animal population, some sort of equation for bacteria or something. It doesn't matter for this case, but this is typically the way that it forms. It is developed, and all we do now is we move the dt over to here and put the p underneath, rearrange it so it looks like in this form, integrate both sides. We get the ln of p, the population size, is e to the kt plus c, and then we can use the properties of where we put everything to the exponent again, and we can get that p is equal to c, some sort of initial population times the proportional constant, which is k, and then it's represented graphically basically by something that looks like this. But it is a first order separable equation, right? Same thing is basically what happens with exponential decay, but it represents a decrease, and that's basically just this part here. And when we look at it, when we do the integration again, all we end up with is a negative here. So this a is to not mark that it's a decay rather than a growth, and same with the m, we don't use p. But there's still the same kind of constant, and in this case, it's actually just to the negative, that constant over time, the value of time. So it is pretty much the same derivation. We could go through the exact same thing by moving over the dt. So dm over m is equal to negative k dt, and then just do the integration of both sides with respect to their respective sides, and we come up with this solution. So that's a nice light Friday morning class for you guys. I will be recording and publishing the start of beam theory for Wednesday's class. That'll be another on your own time, wonderfully recorded video presentation for you guys. And then we'll get back together next Friday for an in-class, and we will talk about both the videos to see if you guys have any questions, as well as we're going to continue on with beam theory and the derivation of beam theory as a function of differential equations. So enjoy your weekend, and I will talk to you in person on Monday for 303. Have a good weekend.